Alright, this is the end of chapter 11. So we're going to look at the different ways to apply anti-differentiation. With the first application of integration is how do we want to find the average value of a function. So we have that function here. What we do is we calculate the area under the curve, so from the rate curve to the x-axis, and then what we do is we divide by the length of the integral, which is the expression that we have. And by doing that, what we figure it out is that value on the side over here. And what it means is that value now I have a rectangle defined by A and B and also by that average value. If I calculate the area of that rectangle, it will be exactly the same as the area of the rate curve over that interval. So kind of useful. Let's say that graph was representing the velocity over a period of time. By applying this formula, the value we read here will be the average velocity or speed over the whole interval. Okay. When you determine the average value, just be mindful of the unit. It will depend on what you have on the x and y axis. As we look at application, we're going to deal with situation with position, velocity, acceleration, or situation with the change of temperature. All right. First example, have a look at this question, pause the video, have a go at this, and we'll come back to look at the working out. Alright, so we have a function, this is our interval, we straight away apply the formula. Okay, it's really for you to practice your anti-derivative over a definite interval. We end up with a value of 4/3. So here is the graph of my function in red. The 4/3 is on the side, so over that interval from 0 to 2 bound by 4/3, which is the rectangle in orange, that area of that rectangle is also the area defined by that integral. Okay, so let's look at other applications. So we're going to look at a few examples when we look at motion. What you need to do remember is from differentiation. When you start with a function that is a position, so a function that is a position, if you differentiate, you will end up with the velocity, and if you differentiate the velocity, you'll get the acceleration. So reversely, if you anti-differentiate your acceleration, you'll get your velocity, and then you anti-differentiate the velocity, you'll get your position function. Just be mindful, I was referring to functions. Here are instantaneous values. The average velocity, average is you need to look at your starting and end values, not what's happening in between. So here our velocity has that following rule. Notice for the x variable or the t variable, it's defined only for the positive values, and there are some preconditions. A body starts from the origin and moves in a straight line. The fact that it starts from the origin tells you that when t equals 0, the position x has to be equal 0. Alright, so those are the questions. So first, you anti-differentiate v, which is 2t minus 4. You anti-differentiate plus constant. You use the initial condition for x, that gives you c equals 0. So we get the rule for the position, which is the answer to part A. For part B, you just substitute t equals 0. You get x equals -3. The negative tells you that when you write a sentence, it's to the left as you go to positive values when you move to the right. Part C, to find the average velocity, you look at the position when t equals 3 and which is negative 3. You do the difference from t equals 3 to t equals 0, and you divide by the duration, which is 3 seconds, and that'll give you your average velocity. Now, to find the distance, you can't take the start and end position. What you need to do is you anti-differentiate your velocity. So let's go to the next one. We have our velocity here, which is 2t minus 4. Hang on. Oh yes, sorry, my bad. It's a linear motion, so you don't have so much to worry about it. Then v equals 0 is, we solve it and we find t equals 2. So for the first 2 seconds, for 0 to 2, it will have traveled from 0 to negative 4. So that's the first 2 seconds will be 4 meters. And from t equals 2 to 3, as the position will be negative 3, it will have traveled 1 meter. So 4 plus 1, that'll give you 5 meters. Okay, so the average speed will be 5 meters over 3 seconds. That will give you your answer. All right. Also notice we've done antiderivative, so instead of doing that work, what you could have done as well is anti-differentiate. That's what I was getting at in the first my first thought is you as the velocity has a rule, you can anti-differentiate over the interval from 0 to 3, divide by the duration, and you will also get your average velocity. So that's another way to determine part E. Similarly, you can also define part D by just doing the antiderivative of velocity. It's not so much covered in methods, but for the students that are doing specialists, that's actually a quicker method to do that instead of just looking around at your x-intercepts and separate the intervals. Alright, next example with motion of a straight line. So you have an acceleration, which is a linear function. You need to find the position and the velocity at specific times. So you need to find the rule. So it's really applying anti-differentiation. Let's look at this. So you have your acceleration, you anti-differentiate once. You use the preconditions is, it tells you at the start you are 3 meters from the fixed point, so x equals positive 3, but because it starts, its velocity is going to be 0 when t equals 0. So you use that and we get the rule for v. Now we can anti-differentiate that to find the position function with a new constant, and we know at t equals 0, x equals 3, so we get the final rules. Okay, am I in the way? Yes. So here you can see the rule here, it's copied over there. Okay, so let's get to actually answering the questions. So we find the position and velocity that's the starting point. Hang on. No, actually that was a question, sorry, but the next question is going to be an extension of that. So look at this question. You have a stone is projected vertically upwards from the top of the building 20 meters high with an initial velocity of 15 meters per second. You have a series of questions asking you time values, the height and the velocity. Now before we get to that, anything to do with gravity, as it is a vertical motion, we treat it as a motion in a straight line. And also what we have to assume is the acceleration, because it's due to gravity, it's negative 10 meters per second. Now you have to assume that the if you go upwards, it's your positive direction. So you start with a equals negative 10, and you will anti-differentiate twice to get your velocity rule and your position rule. You will need those values to determine the constants. I put the questions here, but let's look at, so a is equal to negative 10. You anti-differentiate, it tells you v equals negative 10t plus c. At t equals 0, v is positive 15. So here's the rule for v. Make sure it's correct. Anti-differentiate that again. Again, it's a general anti-differentiation, so you have to add a constant. You start at the top of the cliff, so x equals 20, and we get the rule for x. So we need to keep the rule for x and v, so which is what I did in the next slide. Now to answer question A, the time taken for the stone to reach its maximum height. So the maximum height is actually when v is equal 0, when the stone stops moving. So you solve the equation for v equals 0. It gives you the t value, and that's when it reaches the maximum height. Then for part B, you use this t value, you substitute in your rule over there, you evaluate that, you round it off, and that gives you 31.25 meters. It's positive, so it is above the height of the cliff. Now the time taken for the stone to reach the ground is when x equals 0. So when x equals 0, it's a quadratic, so you will end up with two values, t equals negative 1 and t equals 4. As t is positive, you need to reject the negative value, so you only keep t equals 4, which is the only solution for part C. And to find the velocity, you take this t value of 4, you substitute in your velocity rule, and you end up with negative 25. Now, very important that it is negative, because the stone is moving downwards, so it impacts the ground at a high velocity of 25 meters per second, and it's negative going downwards. Again, sorry, let me move myself out of the way. All right. Another application, so again, it's just to mix up a little different units. So here you have a rule, it's dt over dt is equal to that rule. Just be mindful of the variables used here. So capital T is the temperature in degrees Celsius, and lowercase t is a time in terms of minute. So here what we have is the rate of change of the temperature with respect to time. So in part A, that's what you need to graph, and in part B, you need to take the reciprocal, and what you try to graph to sketch now is the rate of change of the time in respect to the temperature, and that's will help you to kind of explain what the area represents. So let's go with the graphing. The first one is just a linear graph, so let's go with this. So this is a linear graph. Notice how it excludes the x-intercept, because we're going to move on to the reciprocal. So with the reciprocal, t is excluded, but remember it's a hyperbola, so t equals 30 is your vertical asymptote, and the line will get really close to it, but as it is excluded, it's just getting close nearby. Then as you move towards the right, it converges towards the x-axis, which is your horizontal asymptote. We need to annotate t equals 35 seconds and t equals 120 seconds, which is your interval for part C. We need to find the area. So the integral is negative, it's below the curve. So when we do the area, we take the opposite of the integral. We anti-differentiate in terms of the temperature, and that gives us 5.78. Now that area is actually in seconds, because remember here it's the rate of change on the y-axis is the rate of change in seconds per degrees, and along the x-axis it is in degrees. As you kind of multiply the units, because that's your dt, your rule for dt over dt, which is that dt over dt. I know I'm mixing the same letters. You end up with an answer in seconds. So the area represents the duration or the time taken for the liquid to change from 120 degrees to 35 degrees, which is a cool down. Okay, and that was it. 11K, have a read. There's no really questions. It's just a little bit of proofing about the fundamental theorem of calculus. And here it is. We're done with chapter 11. Don't forget the chapter review questions. They're really good questions for you to revise as well. And I'll see you later.